Hello, my name is Carlos, and my professors are Thamy and Andrés, and I'm going to present you the state of art on quenching distance studies. So, introducing the problem, power plants and high efficiency in combustion process to convert the chemical energy into power, and turbines that work with premixed flames generate fewer emissions. But there's a high risk of accidents due to flashback with those premixed flames. And explosions and fire are statistically the main cause of accidents in oil refineries. So there is a big need of equipment that operate with safety. And the flame arrestor is the equipment that offers the safety for premixed flames, avoiding the flashback. And how does the flame arrestor works? Flame arresters forces the flames to quench, and the heat losses reduces the reaction rates inducing the flame to quench when the flame crosses the flame arrestor. And ideally, the flame arrestor should cause the minimum friction loss in flows, and the quench distance is defined as the minimum distance that a flame is able to propagate. So the quench distance depends on temperature, pressure, fuel, and mixture compound. So the objective of this work is to perform a literature review, and in this presentation we have the most important articles available, crossing by theoretical development, experimental determination, numerical modeling, and correlation models. So talking now about the theoretical model, in turns, there is the model quenching by cold wall. It's a simplified analysis that considers a laminar premixed flame which propagates through a slot of two parallel plates, and the energy conservation is applied where the heat from flame is transferred to two walls. And using this model, it's possible to determine the quench distance here in the equation equal to 2 the parameter b, which depends on the temperature, pressure, and the mixture compound, thermal diffusivity, and the laminar flame speed. And in the next slides we're going to talk about more about this parameter b. And Glassman also discusses about the distance quenching, which there's a relation in surface and volume radio. Small quenching diameter and with the quench distance, the higher the surface volume radio is, and then there's a consequence in the number of collisions in the reactions, because as the temperature reduces, the reaction will stop quenching the flame, and varying pressure and temperature, there is an effect in the quench distance. So when pressure decreases, the quenching distance increases, and when the temperature decreases, the quench distance also increases. And the opposite is valid. When pressure and temperature increase, the quenching distance decreases, because it's more difficult to stop those reactions in higher pressure and in higher temperature. So this is the logic made by Glassman. Here there is a figure that presents the quench distance for different temperatures and different pressures, also by the equivalence radio. And for stoichiometric mixtures, for the same temperature and pressure, the stoichiometric mixture presents the lowest quenching distance. So talking about the experimental determination, one of the first works developed was by Friedman in Johnston in 1962, which presents a relation between quench distance and pressure. So he evaluated 4 fuse, isoctane, and the quench distance was bigger for isoctane and reduced in size to N-octane, benzene, and ether-2. So the experiments were made at 100 degrees, and here the images, the figure 2 presents the effect of pressure. Here we have in the first image we have atmospheric pressure, and reducing the pressure, the value of the quench distance got higher, right? Recently, Lauermann studied the influence of the flame speed on quenching distance, and the experiments happen at ambient temperature and 1 atmosphere. So he tested different fuels with some different equivalence radio, and he employed the fast Schlieren imaging to evaluate the flame between the parallel plates for methane, ethane, and propane. And as we can see, for higher flame speed, the quench distance got higher. So the effects of the turbulence, it's seen here because the flame was accelerated, and it turns the heat transfer much stronger for those cases which the turbulence was in. So here we have the parameter B, which was calculated using the experimental data from this work, and as you can see, the parameter B has a big influence from the flame speed and for those different fuels. Gilberti in 2020 experimented the quench distance for cryogenic temperatures, evaluating at 1 atmosphere for methane air, and he uses a flat plate and tubes for his experiments, and the quench distance for the ambient temperature was 0.17 millimeters, while for a cryogenic temperature the quenching distance got higher, 0.34 millimeters, and for the cases of 2, for the ambient temperature it was 2.5 millimeters, while for a cryogenic temperature 3.5 millimeters. So for the lower temperature the quenching distance got higher, and this temperature in this case is the temperature of the wall, which surface where the flame propagates. And as we can see, for those lower temperatures, the difference of temperature between flame and surface are higher than for those cases in the ambient temperature. So it is easier to stop the reaction rate, so the quenching distance can be higher. So now talking about the numerical modeling, Henrique in 2005 presented the main equations that are employed, which are the mass conservation, the species conservation, the momentum conservation, and the energy conservation. Those equations are well applied in combustion modeling. And Kudryakov in 2011 studied numerically the hydrogen, and he wanted to predict the flame quenching, and he employed the one-step reaction for hydrogen, and he evaluated the effect of the mesh in his sketch, which is presented in in figure 5, the characteristic diameter was 0.3 millimeters, and the coarse mesh had 1,134 elements, while the fine mesh had 10,354 elements, and as a result, the coarse mesh quenched the flame, while the fine mesh did not affect, and employed the equations presented by the previous work by Thierry Poisson, and he concluded that the mechanism, the chemical mechanisms, maybe influence strongly the results. And a few years later, Lauermann studied the same problem, but he employed the Thales mechanism for hydrogen, employing 19 reactions. The global mechanism did not predict the flame quenching, only locally close to the obstacle, while the Thales mechanism, the flame could not pass through the obstacle, so the flame quenching happened. So his big conclusion is that the Thales mechanism is able to better represent physical phenomena, because as it considers more species, the thermodynamic properties are better calculated and better representing the phenomena. And talking now about the empirical models and correlations, Friedman and Johnston in 1950 studied the propane, and his correlation for propane was varying the temperature for 300 Kelvin to 652 Kelvin, and he uses in the first moment plates heated, and in the second moment the initial gas was heated. So in his correlation he used a power law, which the quench distance is related to temperature and exponential number, which is for the lean mixtures 0.85, and for stoichiometric and rich mixtures 0.5. And plotting the quenching distance for propane using these exponential numbers, constants, which we can compare the experimental data available for propane at flame speed for 50 meters per second in the study of Manhattan, and the value is almost the same, which was 1.5 millimeters. So we can believe that this correlation is useful, because it can predict the flame quenching. And another empirical model was developed by Takizawa et al. In 2015, which tested 11 fuels with air relating to the flame speed for 11 fuels. In here the figure 9 has all the fuels tested, and you can see that once again the quenching distance uses a power law equation to relate the specific measurement to the quenching distance. So the conclusions is that doing this work, it was possible to enhance the understanding of quenching distance, and quenching distance depends on the fuel, on the equivalence ratio, and the initial temperature and pressure. The theoretical model uses simplified considerations. The stoichiometric mixtures and rich mixtures, when the equivalence ratio was between 1 and 1.1, presented the lowest value for the quenching distance. A dimensionless parameter B was calculated using experimental data and seems to have dependence on to flame speed. A detailed mechanisms and refined meshes shows better results in numerical simulation. Especially, the detailed mechanisms are able to better represent the physical phenomenon due to the quantities of species involved. And for hydrogen, the detailed mechanisms predict the flame quenching. And experimental data fitted well with correlation that involved power of the temperature, pressure, and flame speed. And the quench distance predicted by correlation also agreed with experimental data. Moreover, this literature review guides us to keep studying the quench distance, especially for an experimental and numerical approach. We didn't find studies about quench distance of ethanol, which is an important field in Brazil. So thank you so much for you.